today I will be sharing with you how we are able to get near exact energies with very compact wave functions. So before I begin, I must mention that this work that is going to be presented here is part of a bigger work that is published on Archive. And so I would advise anybody who is interested more in getting the bigger context of the work to visit that paper, because this is just a small section of the work. But essentially what we are trying to do is we are trying to use this method that I'm going to present here to create benchmark energies for another method that is discussed in detail in the paper. But so we need to understand what is quantum chemistry and why we need quantum chemistry in the first place. So quantum chemistry really is just a study of the behavior of electrons in atoms and molecules and systems. And just by understanding the behavior of these atoms, we can be able to predict a lot of thermochemical properties, including but not limited to energies. And a very classical example is you can go to the lab and use a cisplatin, for example, and do some reaction where you can get the energies at point A, at point B, and at point C. And with those energies, you can actually get things like the reaction rates as well as thermodynamic properties like Shidok potentials and bond dissolution energies. But the whole point of quantum and electronic structure theory is what if you could actually get these energies without necessarily doing the experiment in the lab. And that is known that it is possible for a very long time. And so one of the founding fathers of quantum mechanics, a guy named Paul Dirac, said that the math that underlies all of the chemistry is actually known. The only problem is that it leads to some mathematical equations that are not very good looking. And for example, we can get the energy of a system as well as the probability distribution of electrons in that system just by having the Hamiltonian act on the system's wave function in the so-called time-independent Schrödinger equation. But if we look at the Hamiltonian, specifically the non-relativistic Born-Oppenheimer Hamiltonian, it has three main terms. It has the electron kinetic energy term, so this is just measuring the kinetic energy of the electrons. This is only dependent on the index of the electrons, so this is possible to achieve. It also has the nuclear electron attractive potential. This also depends on the electron index because we are assuming an approximation called the Born-Oppenheimer approximation, which tells us we assume a static nuclei. And so this term also only depends on the electron index. So this is also solvable. But the third term is measuring the electron-electron repulsive potential, or the so-called inter-electron energy. And this term depends on the index of the two interacting electrons. And that is the beginning of the so-called quantum many-body problem, because the moment you have two electrons, you will need to find the index of those two electrons. But because the electrons are dynamic, they are not static, that term becomes really hard to find. And so over the past years, theories have been developed to try and model that term to as high accuracy as possible. And the most accurate approximation to that term, which is actually exact, is the so-called full configuration interaction. And so full configuration interaction tells you for you to model the electron-electron interaction energy, you have to consider all the possible ways in which electrons can arrange themselves in a system in all the given orbitals. And for you to do that, you will have to include all the possible excitations that the electrons can take in that system, which means in that case we include all the zero excitations, all the single excitations, all the double excitations, up to n excitations. And so the full configuration expansion for the wave function will just include all the zero excitations, singles, doubles, triples, all the excitations. But as you can already tell from that diagram, as you include all the configurations, because the configurations actually grow exponentially the number of electrons, this becomes very hard because you just can't diagonalize and actually construct in the first place the Hamiltonian in such an expansive space. Actually, the largest system that this has been done so far is propane, which as you can tell is not very chemically useful. But then the question comes in, do we actually need all the configurations in this case? Do we need all the single excitation configurations? Do we need all the double excitation configurations? And the answer to that is no, we actually don't need all the configurations. So this work here was done by Rossi a couple of years ago, and this was a calculation on nitrogen, the nitrogen dimer. And what they realized is that for a system with over 967 billion total configurations, you only need about 3,000 of those configurations to model about 98% of the total energy of that system. And so the idea came up, what if we could only select only those configurations that actually contributed meaningfully to the energy of a system? And that has been implemented in a couple of methods. For example, the so-called configuration interaction singles and doubles, which basically does the first excitations and the second excitations and then truncates the wave function. But as you can tell, that is not as accurate, because being a higher order excitation does not necessarily mean it's not a meaningful contribution. And so the idea here is we could actually do the selection automatically, which will be much better. And that is exactly what we are doing with this algorithm that's called CIPSI, which stands for configuration interactions using a perturbative selection made iteratively. And so the CIPSI algorithm is a typical selected configuration algorithm. And what it's doing is it's starting from some single reference configuration, in this case H4 configuration, with some energy E naught. And then it's computing the approximate energies that results from all the other missing configurations. And then it only selects all those configurations that results from the largest approximate errors in the energy, where in this case you're only exploring the first or the single and the double excitations at every point. And then you add those configurations to the reference configuration, you diagonalize Hamiltonian in the base of the reference configuration, you update E0, you assess whether the energy is converged, where you can define that in terms of whether you have the maximum number of configurations or you have the minimum correction, and then you exit or iterate depending on whether it's converged or not. And so a diagrammatic representation of that is there. So what is happening is you're starting from some single reference, the E0 in this case, and then you are expanding to all the to all the excitation, and then you only select the meaningful. So the black dots are the meaningful. The others are the non-meaningful. In this case, they have very small contribution, and then you go and you expand the space. And how we are able to compute the approximate error as a result of missing some configuration is with the so-called perturbation theory. So at every particular configuration, we do a second order perturbation calculation, and the total sum of the total perturbation to energy added to some calculation will just be the sum of all the perturbation corrections of all the configurations added to the system. And the idea here is if you have 0 E2 or 0 perturbation correction, it means you are effectively at the full configuration interaction, because that means you have not found any meaningful contributing configuration to add to the reference subspace. And so because it is not possible to reach the full configuration wave function, because remember you're only selecting some determinants, some configurations, which means even though it's not contributing as much, it still has some contribution. What we do is we extrapolate the E naught in this case, which is the variational energy, as either E2 or some renormalized version of E2 goes to 0. So in this case, gamma is just a renormalization factor. And the reason why we need the renormalization is because this is the path that E2 follows. E naught follows as E2 goes to 0, and that is the renormalized version. And that up here is the equation followed by this path. So that is the so-called nonlinear extrapolation function, which I won't get into much detail how that comes about, but it's a whole lot of math. But basically, we need to normalize that if you have to do a linear extrapolation, which is what almost everybody does in the industry at this point. And so one of the first things we did with this algorithm was to test its accuracy. And this graph right here shows its performance with CIPSI. So basically, there's a difference between our energies with FCI energies. The red curve represents our linearly extrapolated energies, while the blue line represents the variational energy. And you can tell both the linearly extrapolated and the variational energies all lie within the chemical accuracy. And so we were certain enough that this algorithm is actually pretty accurate. And so we went ahead into our systems of interest, which in this case were chains of hydrogen, chains of 19 hydrogen and 20 hydrogens. And so this is a chain of 19 hydrogens, and this just shows the energy calculations. And as I mentioned earlier, all the linear and the nonlinear extrapolations is supposed to be, in theory, perform similarly and give the same energies, which was the same, the case for H19 in this case. So basically, this just shows the performance of CIPSI alongside other methods. And this is the graph that we were actually looking for, where we are benchmarking other methods against CIPSI, because this is just the difference between the other method and CIPSI, just to see which of the other methods performs much better. And one of the things we noticed was that a variant of coupled cluster method, the GCCSGT, which is another method we used in this case, performed quite consistently with CIPSI in that it was always around 10 millihartz higher in energy than CIPSI. And that was true for all the other points, except one point for our H20 ring, where we realized that it was flipped. Now CIPSI was the one that was about 13 millihartz higher in energy than the coupled cluster point. and that signaled to us there was a problem with the linear extrapolation at that point. And so we went ahead and did another calculation with another reference method called DMRG, and DMRG gave about 30 millihartz lower in energy than the value we had for CIPSI. And so we concluded that the linear extrapolation at this point was failing, because our nonlinear extrapolation, of the same point gave some energy that was pretty consistent with what we had seen for all the other methods, which was around 10 millihartz lower in energy than the coupled cluster variant. And so this also is a graph that's showing the energy comparison of CIPSI with other methods. It's hard to see, but it performs quite well. It's much lower in energy. And so this is the graph for the benchmark of the other method against CIPSI, where in this case the y-axis is just the difference between the method and CIPSI in this case. And so we ascertained that for all the other points except this particular point, the linear and the nonlinear extrapolation were well within 3 millihartz of each other. But in the text, we actually report the nonlinear extrapolations with alpha minus 1 point. So in this case, alpha is the total number of iterations. So for a 20 iteration calculation, we do the nonlinear extrapolation with 19 points. So in the future, we'll be looking into using the algorithm. Well, we are actually using the algorithm to do calculations on a little more chemically meaningful substances like CO2 and O2. And we're also looking into doing excited states calculations with the same algorithm. And we see this as a starting point for the development of other methods, like a method called auxiliary field quantum Monte Carlo, that I won't get into detail, but we see this as a starting point in that we can use these wave functions to better develop the method. And we also seek to interface this particular algorithm with already existing codes like PySCF and a locally developed 2C in the lab, just to try and model other chemical phenomena like strong correlation. And so in conclusion, what we are trying to do here is quite non-trivial, because it's very hard to apply CIPSI in chemistry right now, because even though it's cheaper, it's still a selected configuration algorithm. So it scales exponentially. And so although it might not be very applicable in chemistry right now, we see this particular algorithm as a core ingredient in the development of other low scaling methods that seem to have some pretty interesting accuracy. And so like this graph right here is just a graph that I stole from some paper, but it's basically showing the development of AFQMC, where the weight change basically shows how if the quality of the trial function we use something called trial function, where in this case we are trying to use CIPSI wave functions as the trial for that, and we expect that to get better and better as we use CIPSI in this case. So I would like to thank the SHILAB for the support, as well as the Rice Department of Chemistry, the Rice Department of Research Computing, as well as Oak Ridge Computing Facility, because we use their supercomputers for these calculations. Thank you so much.